So again, I'm Bastani. Today I'm here to talk to you about graph data modeling with Neo4j. So this is the agenda we'll be going over today. So what is a graph database? An introduction to graphs. An introduction to the labeled property graph data model. We'll do an introduction to Cypher, which is Neo4j's declarative query language. We'll also do a tour, a live demo of the Neo4j browser, which is how we actually interact with the database over a browser. I'll do an introduction to graph-based modeling. I'll walk you through some of the aspects of actually designing a graph for your database. And then I'll go over some graph data modeling guidelines, things you should do, things you shouldn't do, some best practices. And then finally, I'll talk to you about how to author a graph gist, which is a project that we've created to allow you to articulate some of your use cases without having to download the product, without having to install any software. You create a markdown file and it renders into a live, actual, kind of like a white paper proof of concept that uses our database in a website. So it generates a website with some queries. Cool. So first let's start by answering the question, what is a graph database? So the graph database is a NoSQL database that allows you to store and manage your data as a graph. And so if you're not familiar with what a graph is actually just a data structure that has nodes and links. So you have these nodes which have some directed arrows, and those arrows are relationships that kind of describe the interaction between nodes. So a graph database allows you to easily store and manage this kind of data structure. So as you see here, there's a little example graph here where you have you at the center and then you have your friends. So that's a screenshot from our browser. So let me introduce you more to the concept of graphs. So what are graphs? So these aren't graphs, these are charts. So we have to disambiguate because a lot of people call them graphs, and that is the proper name for them. But we like to say at Neo that these are just exclusively charts, so that no one gets confused. Okay, so what do graphs have to do with data? So here we have an example of a graph, and you see that you have some directed arrows, which have some labels on them. Those are relationship types. And you have some people, and you have a book. So these actual rectangle, circle things, those are nodes, and the arrows are relationships. So here we have John, who's a friend of Sally, and we see that Sally's also a friend of John. And we see that both Sally and John have read the Graph Database's book. So it describes some model, some abstraction of the world, and puts it into an easy way to articulate. So the relationships provide some semantic context for you to actually describe some arbitrary domain. Now, if we take that further and we actually assign some key values to these entities, these objects, we have now something that we can articulate more. So we have now added age on Sally and John. So we see that John is 27. We see Sally is 32. On the relationship, we have another key value. So we see the date that they've been friends since. And we see, too, some information on the has read relationship. So we see that John read it on February 3rd, 2013. We see Sally read the book on February 9th, 2013. We also see the ratings that they gave it. So we see John gave it a 5, and Sally wasn't so impressed, she gave it a 4. We see some more information about the book. So we see this is the Graph Database's book, and we see the authors, Ian Robinson and Jim Weber. So how does this contrast to the relational table model? So here we have two tables. We have customers and accounts. We have Alice, who's a record in the customers table. And we have a couple accounts. And so the problem here is how do we attach Alice to her accounts? Well, if you're familiar with relational databases, you know that there's a third table in the middle, which we call a join table, which joins these records together. So we'll call that customer accounts. And so we see here that we have a mapping from Alice to her accounts in that table. So that's how you would do that. Do something very similar in the relational table world. So now that we've gone over the contrast between relational and the graph-based data modeling, let me introduce you to what the label property graph data model is. So that's kind of a mouthful, but what that means is that we actually have this model that Neo4j is based on that sharply contrasts from other graph databases and from RDF. We have our own kind of proprietarily designed data model, which we call the label property graph data model. It has 4 basic building blocks as of today. We have nodes, relationships, properties, and labels. So I'm going to go over each of these and kind of the rules that apply to each. So first we start with nodes. And so here we have an example graph, and you see the blue circles, those are nodes. They can contain key value pairs. And they're used to really, they're your entities where you're going to actually describe the interactions between them using relationships. So some more rules. Nodes can contain properties, which are key value pairs. They're Java primitives. Neo4j is written in Java. It runs on the JVM. You can also have arrays, which we call collections. And null is not a valid value, which is an interesting thing because on the graph you have more of a semi-structure. Nodes don't have to have the same keys on every node. In a relational database, you have these keys that are replicated across certain database or certain tables. So you have these key markers that are the same. So you have foreign keys, you have primary keys, and they have this strict schema that's enforced. You don't have that in the graph. You have a semi-structure where not all nodes have to have the same key. So when you query a node and you're looking for a property name and it doesn't exist, you get back a null value. So what about relationships? So here you have relationships which are directed. They exist exactly between 2 nodes. In our property graph data model, you can only have relationships that are directed one way or the other. You can't have bidirectional relationships as a rule. So here we have a couple example graphs. So here we have Peter and his friends, showing that nodes can have more than one relationship. We also have Peter and Lucy. We see that Peter is a friend of Lucy, and we see that Peter is also a colleague of Lucy. Articulating that nodes can be connected by more than one relationship. And then self-relationships are also allowed. Here the example is Peter proposed to Peter, or Peter voted for himself. Would be a good example of self-relationships. So some rules about relationships in the property graph. Every relationship has a name and a direction. So we have one type, so we call it a relationship type, that exists between the 2 nodes. Some of the things that it does, it allows you to structure your graph more. So for the example, you have people, and then you have a relationship between people, can be something like friends. So if you wanted to find the friend of somebody, you can start at a person node, and then you can traverse outward with that relationship type. Relationships can also contain properties, just like nodes. So what properties on relationships are used for typically is to qualify the nodes to give them some type of context or weight. So for example, between 2 nodes, if you were to diagnose maybe a symptom, so you had a diagnosis model where you had people with symptoms and they wanted to see what their afflictions are, and they're describing their pain from maybe a symptom. You can have a relationship that has a value, a weight, that describes perhaps how much pain they have. Another rule is that no dangling relationships are allowed. So you can't delete a relationship if it's connected to some nodes. You have to delete the nodes, or vice versa. So you can't have a relationship hanging out there with no node attached. And then finally we have labels. And what labels are used to do is to group nodes in your graph together. So it parallels, if you've used Gmail in the past, you'll notice a similar feature where you're applying labels to your emails. So it's a very similar concept. We allow you to categorize groups of nodes within the graph to give some meaning to them. So the example here is we have to the left person, who's also an author. In the middle we have book, and to the right we have person for people. So some rules about labels is that you can have 0 or more labels. It's not required. You can have as many of them as you want. They're used to represent roles, again, like a user, a product, or a company, which groups nodes together. And also, it allows us to associate indexes and to assert constraints on that set of nodes. So for example, if you wanted to index a property of this set, you can specify within the person index or the person label, I want to index the property name. So it allows you to do that. It also allows you to assert unique constraints. So if you wanted the user ID property to be unique on a user role, then you can also do that. So those are the 4 basic building blocks of Neo4j in the label property graph data model. So you have nodes, relationships, properties, and then again labels. Okay, so now that you understand how we actually store and manage this data, what it looks like, what are some of the rules, let's go over Cypher. So if you remember from earlier, Cypher is Neo4j's declarative pattern matching language, which has a very SQL-like syntax. And so this is how most people would want to interact with their database, how they want to actually query data. But it's specifically designed for graphs. So you have the power of a SQL-like syntax, which you may be very familiar with, but you also have the power of graphs involved with that. So how does that work? So I like to say that it's all about patterns. And what a pattern is really a configuration in your graph. So here we have this pattern where A is directly connected to B and then C. And we see that B is connected to C. So this describes some pattern that exists within our graph. So what does that look like? So here's our pretty picture of what maybe our graph looks like in our database. And we see that same pattern here where A is connected to B and C and B is connected to C. And we're going through, Cypher goes through the graph and it finds all instances of this pattern that exists and it returns it back. So it goes through all the configurations and finds that pattern. So why is that useful? Well, A, B, and C is an abstraction, but here, if you were querying an actual domain, maybe you have A, B, and C are actual roles or labels that exist on the nodes. So maybe if it's a movie domain, you have some movies, you have some actors, and that allows you to find all of these things using some type of pattern. So how do we do this? What does the query language actually look like? So we do it using text art. If you're familiar with ASCII art, actually these pictures that you see maybe on Twitter or in chat rooms, that text that looks like an image, that's exactly how we thought about it when we designed it. So here we have A directed to B as a graph. Well, in Cypher, we have the text in ASCII, A is directed to B. And so that's how we describe the patterns. Okay, so let's look at an actual real Cypher query. So here we have a real Cypher query, which kind of looks like SQL, but we're using a clause called match. And what match does is it goes and it matches that pattern in the graph. And then in the return statement, you're just returning the nodes here. So here, we're looking for A or B are connected in either direction. So we're not specifying a direction here. And then returning back those 2 nodes. Now, if we wanted to specify an actual direction, we can do that as well. So here we have matched the pattern A is directed to B, and then to return back A and B. So again, what does that look like? So here's our pretty example graph. So you see the same pattern here that we look. So very, very simple. So what about relationships? So relationships exist in these square brackets, while these nodes, they're in parentheses. So the parentheses kind of describe this little circle, which is a node, and then the square brackets here describe the relationship. And so these identifiers, A and R, they're used to actually store the results from a match and to be used later in the query. So here we have 2 nodes and 1 relationship again, and here we're matching A is directed to some other node. We're not specifying the node because we don't need to use it or return it, so we're just saying we want this pattern, and then to return back A, and then the property name, and then we're using a function in Cypher called type, which works around relationships, which actually returns you back the name of the relationship. So an example of that, if we had a relationship type that we've named acted in, here we have actors who acted in a movie, and that would look like this. So we have now this relationship type, any square brackets. We use a colon here to separate out the identifier, which would be on the left normally. If you don't need the identifier, you wouldn't specify it, but you still use the colon. And then a Cypher query would look like this. So we have match A, the actor who acted in a movie, and return back the actor's name, and then the title of the movie that they acted in. So you can also return back the properties that exist on the relationship. So here we have roles. So what role did the actor play in the movie? And that exists as a property on the acted in relationship. So we're returning back the roles as well. So where it gets interesting is that we have the concept of paths, which are these multiple hops out. We have a variable length traversal, which you can specify with a range of how far you want to hop out. And this is really powerful because it allows you to do friend of a friend queries. So figuring out the friends of a friend, which can be very complicated or complex on a relational database, we allow you to just specify a pattern and then to return it that way. So here's the 3 hops. We have A is directed to B, and then B is directed to C. So again, we're matching this pattern in the graph. That's what it looks like. We can also change the direction, so you can actually match any pattern. A is directed to B, and C is directed to B. And again, here's what that looks like. So now let's actually get into something real. So if we had a movie domain again, we wanted to answer a question. So the question here we're wanting to answer is who acted in a movie and who was the director of that movie? So here's what that query would look like. We have match A acted in M, which is actor acted in movie, and then we have another one which is D directed M. And to return back the name of the actor, the movie's title, the director's name. So just like before with A, B, and C, we're finding the labels that are applied to the nodes. So we have actors, we have movies, we have directors, and then we're matching this pattern in the graph and returning it. So what would the results look like? Here we have tabular results that are being returned. So you see that Keanu Reeves acted in The Matrix, and the director's name of that movie was Andy Wachowski. So we support aggregation functions as well, similar to SQL. Some examples, we have count, we have min, max, average, sum, and collect. And we have many, many more. We have some statistical functions as well. You can look online in our documentation to get all of the functions that we utilize for aggregates. So an example of using aggregates in Cypher looks like this. We're answering the question, which actor and director work together the most? So here, I'll break down this query. We have match A acted in M, D directed M, and then returning back the name of the actor, the name of the director, and then we're counting on all results to get the count. So it groups these together, so it counts the duplicates A and D with the proper name, and then it orders by that count, descending, and then limit by 5. Okay, so let's talk a little bit about graph traversals, getting from point A to point B or C. So we call this the all nodes query in Cypher. So you have match n, return n, which matches every node in the graph. And then we have a where clause, which is used to, as a constraint, say, okay, I want to match n, but I only want to get back those nodes that have the property name, and that property equals Tom case, and to return back that node. So this filters the results, just like SQL. But we allow you to do this in 2 ways. So we have something called the concise syntax, which allows you to specify some key values in the match clause, so you don't have to use a where clause. Where is not deprecated, it's still very valuable for range operations and other things. But this is just a way to say, okay, I want an exact match back on a couple properties of the node. Why is that useful? Well, if you want to start somewhere and then traverse outwards, you have to find that node first. And so it's easy when you're matching these long patterns where you have this concise syntax that says, okay, I have Tom Hanks, now I want to find all the movies that he's acted in. And then you can also add a label. So again, labels are these roles where you can have multiple roles associated with nodes. And we see here that we're looking at the set of nodes within this graph. We can have millions of nodes in the graph. But if we just look at a subset in that graph of actual people, then we're taking a smaller set of that total graph. So we're decreasing the search space so that we can actually spend less time looking for things. And so that's why labels are powerful. And from there, you can use a where clause for tom.name equals Tom's. So again, pretty graph, T for Tom. Okay, so then putting these two concepts together, here you have the label people, you have or person, you have the label movie. So in this match clause up here, you're looking for Tom Hanks' movies. So you're saying match Tom with a label person, and then get the relationship type acted in, and then movie with the label movie. And then here we're using where tom.name equals Tom Hanks, and then we're turning back the title of the movie. And then using concise syntax, we only need to use 2 lines. We don't have to use where clause because we can actually specify the key value for Tom Hanks on name. So this makes it a lot more expressive, and there's some performance benefits as well. So what does that look like? So here we have Tom. We're starting with Tom, so we're getting the T node first. And then we're traversing outwards from T to the M nodes, which are movies. So here we want to find all the directors who worked with Tom Hanks. So very similar query. We're breaking it into 2 patterns. We have 2 triples here. The first triple is we're looking for Tom Hanks and the movies he's acted in the first line. In the second line, then we're also specifying with a comma that we're reusing the movie identifier, and we're saying also get the director that directed that movie, and to return back the director's name. And so this is the final pretty graph that I have to show you, and then we'll actually get into some code. So we have T, and then this is the traversal pattern that we're specifying. So we have T, and then M is not specified because we don't care about that node. We just care about the directors who directed those movies. Cool. So now let's actually look at the browser. Let's do a live product demo of Neo4j Browser. First, let me explain a little bit about the browser. So in the Neo4j Browser, it's basically just a web-based shell, a REPL if you will, that allows you to execute queries over a browser and to visualize results. So that's the basic rundown. So we have graph visualization bundled into this, so when you return nodes and relationships, you can actually play with that data, which is great. To get started, you can also look at one of our tutorials that's actually in the browser that allows you to create a sample data set, which we looked at today when I was explaining how Cypher works, which is a movie data set. And again, you can display this data. So let's go and take a look. Okay, so here's the Neo4j browser, and you see at the top here, we have a console. This is where you type in queries. We have history, so if you hit Control up, you can get a history of previous queries. Also, you can run these queries, so I'll show you an example. Let's do some live coding here. If I do the all nodes query, which is match n, return n, hit enter. that executes the Cypher query, goes to the database, matches that pattern, returns back the results. Nothing in the database, so no results. So let's change that. Let's go ahead and add some data. So if you look here in the intro, you see that you have jump into code with a mini graph app. If I go ahead and I click on the movie graph, it opens up this clever little tutorial, which walks you through a basic problem and how to solve it using a movie graph. So it walks you through how to solve the baking path, which, if you're not familiar with, it's how you're related to somebody else on the planet by how many hops. So if I walk through these slides here, I go to the next one. I'm not going to walk you through all the tutorial. You go ahead and you can click on this ugly text, and then that pops it into the console, and you can go ahead and execute this, and it creates this movie graph. So now, if I use the history, which control up, I can go back to the all nodes query, and I can execute it, and now we actually have some data. So here you see a lot of stuff, but the yellow nodes are people, and the purple nodes are movies, and the relationships between them describe the relation between the nodes and the labels. So what if you don't want to actually look at this pretty graph, and you want to actually look at some schema to see what's related and how? If you go over to the left here, we have these panels. You click on the star, which is your save scripts. We have a default in here, which is what is related and how. So if I go ahead and click that, it loads this query into the console, hit play, and then we get a tabular result, which then you can just easily read and see what's related and how. So for example, we have people who have acted in a movie, we have people who have directed a movie, we have people who have produced a movie, wrote a movie, we have people who follow other people, and we have people who have reviewed a movie. So something very similar to IMDb, that's the data set that we have in here. Cool. Now let's try some of the queries that we went over earlier. So if I wanted to find all the movies that Tom Hanks acted in, I can use the concise syntax. So we're matching the person named Tom Hanks with the relationship type acted in, directed to M, with the movie label. And then there's a couple things we can do here in the return statement. If we wanted to see some visual results, we can actually just return all, and then control enter to execute. And here are all the movies that Tom Hanks has acted in. Now, if we wanted to show some tabular results, we can just change that to return back Tom, his name, and then m.type. Then you get the tabular results. Two, we can see what roles that Tom Hanks played in these movies by adding R on the relationship and then returning back r.roles, which is a collection, an array. So then you can see the role that he played in the movie. So that's the basic idea of a graph database, Neo4j, some examples of how you're actually querying this graph data. So Facebook's social network is a giant graph that describes the behaviors between people and people, what they like, what they do, where they're at, some pictures. And graph search allows you to just type in something, you don't need to know query language, and it figures it out. So here, in this example, we have the Facebook graph search query, which is sushi restaurants in New York, that my friends like. So what that graph might look like is here you have Philip who's smiling, and you see that Philip only has 2 friends. You have Michael and you have Andreas, and you see the likes of Andreas and Michael. You see that they like, so Michael likes iSushi, we see that Andreas likes Sushi Sam, and we see that these restaurants here that are in teal they actually serve the cuisine sushi, and they're also located in New York. So that's the basic idea behind graph search. It translates this natural language representation into this graph. And so how would you do something like that in Cypher? So here we have the Cypher query that does this exact thing. And so we're looking for the person named Philip. We're getting Philip's friends. And then we're seeing all of the restaurants that Philip's friends like. And then we're looking at the restaurant to see, first, is it located in New York? And does it serve sushi? And to return back the restaurant's name. So here's actually another pretty graph. So that Cypher query will then translate that into a traversal, and it goes out and finds it. So that's just one real-world use case. So now that I've shown you a use case, I've talked about Cypher, I've talked a little bit about the graph property data model. Now let's finally get into how do I get up off the ground and start actually modeling my domain as a graph. So the first and most valuable instruction that I can impart on you is to start with a whiteboard or a piece of paper, but a whiteboard's better because whiteboards are easy to articulate some domain, and you probably have done something very similar to this in the past. So you can take this exact model here and you can actually translate that into a graph that you store and manage using Neo4j. So here we have an example of maybe a social network where we have two people, Adam and Sarah. We see that Adam and Sarah are friends, and we see some behavior from Sarah. We see that Sarah likes this piece of content here that's called LOL Cat. We see that Sarah also commented funny on that piece of content. We see that Adam originally shared it. So that is a property graph data model itself. So that can be transposed directly into Neo4j, and then you can query and ask questions on this data model, like who are friends of Adam and the content that they've commented on. And so that's the basic idea behind starting with a whiteboard. Now let's look at another domain, the one that we are very familiar with today, which is the movie data set. So here we have a whiteboard drawing, which you have actors, you have directors, and you have movies. So you see the relationships between these actors, the movies that they've acted in, and you see that both of these movies were directed by Bastani, being Cloud Atlas and The Matrix. So again, that is a property graph data model. So you can take that and put it right in the database and start querying on it. So the next piece of advice I can give you is to model incrementally. With a graph data model, it's really important to iterate your design. Because you have these questions that you want to answer, and you know maybe these questions up front, but maybe you have the business who's asking you questions that you're not predicting, that you don't know yet. You're not actually accounting for these future questions. And so what a graph allows you to do is to model incrementally fairly easily, as opposed to a relational database, where if you wanted to add a property, you have to actually go through this process, and it's kind of dirty if you're familiar with it. But there's really no easy way to do it in a relational world. But with a semi-structure like a graph, it's pretty easy just to add a property. So here's our movie graph again. And here are some of the some more information that help describe this model. So we see that we have Tom Hanks and we have Hugo Weaving at the top. We have some properties here like nationality. We have the awards that they've won. We have, again, the roles that they have acted in, the movies that they played in. We've added genre as a property. And also on the director, we have the same as the people up top. So nationality and the awards that they've won. So some graph data modeling guidelines. What do I do? What do I not do? So in a graph, you have this problem commonly. You have symmetric relationships where you have, for example, here you have two people and the relationship between them. You see that Sarah is a parent of Eric, and you see that Eric is a child of Sarah. And so when you're modeling this out, we ask you to choose between one or the other. You can certainly use both, but that increases the amount of relationships total that you're traversing in some cases. And so it's really simple to actually just infer these symmetric relationships by saying one or the other. And then the Cypher query looks like this. So in the case you chose parent of for all of your relationships between people instead of child of, you would then query the same pattern, but you would just return different results. So if I wanted to find the child, the match is find Sarah, parent of child, and to return child. To find the parent, it's match parent, parent of child, and then just return the parent. So what about bidirectional relationships? So the example here you have is Eric knows Ernie, Ernie knows Eric. How do I model that out if I can only have one relationship that's directed either way? Well, you would use a query that ignores this relationship direction. So we ask you not to do this, that's redundant and unnecessary, and instead, just use one or the other. It doesn't matter which, just use one or the other. And then when you're querying for your nodes relationship, don't specify a direction. We allow you to do that, which will get either or. Okay, so what about qualified bidirectional relationships? So what if you need to have bidirectional relationships because these relationships describe some quality or strength of the actual concept between the two nodes. Well, here we have the example. We have two people, and we see that Lucy likes Peter, but poor Peter, he loves Lucy, and she doesn't reciprocate. So to model that with actual property, you would actually have a strength property on the relationship, which in your application layer, you can have a rule that describes what's the value. If strength is 5, does that equal love? In this case, yes, it does. Another question that I get frequently is properties versus relationships. When do I use a property and when do I use a relationship? So here we have an example of a person who has multiple addresses associated with them. And so here in this example here, this giant node, which would be the center node up here, we have Patrick Scott, age 34, and we have these properties which are complex value types. So we have home address and we have work address. Well, that's probably not the best way to go. That's more similar to RDF. In the property graph, you would just model these addresses as nodes with their own properties and have a relationship attached to those nodes. So when to use relationships? So you should use relationships when you need to specify some weight or quality of the connection between nodes. So that's first and foremost. Then also, if the value comprises a complex value type, for instance an address, then you're going to want to use a relationship. Another example is if you have a value where multiple people share that, then you're probably going to want to create a node for that and then attach a relationship. So for example, if you have multiple people living at the same address, that's very valuable to have as well. So some examples of that is find all my colleagues who are level 2 or above in a skill, which is a property value, and that we have in common. So that would be something like LinkedIn as an example. So LinkedIn is based off of a graph model as well. Also, find all the recent orders delivered to the same delivery address, which would be a complex value type. So here's that LinkedIn graph model. So what we're trying to solve here is that we have this social network of people, and we have the roles that they're in, and we have the skills that they have. I'm not modeling the actual their jobs here, but this graph can expand to include that. But here we have Ian, Lucy, and Bill. We see that they share a set of skills, Java, C#, Neo4j, and Ruby. And we see in the relationship type here has skill. We see the level that's associated with that skill, showing how strong they are with that skill, how many times they've been endorsed on a social network. And then also we see that they work for the same company. So when to use properties instead of relationships? So when there's no need to qualify the weight or of the relationship to the nodes, then there's really no need to use it. It's a simple value type like a color, then you just want to use a property. So some examples of that is that you have these projects on GitHub that have been written by contributors to my projects, and they use the same language, which would be a property value. So also we have this concept of relationship granularity. So if you're familiar with graph databases, you might have heard of RDF, which differs a lot from the property graph data model. So you have these two kinds of graphs. So here on the left we have this coarse grain model where all the relationship types are the same. So we have people, we have addresses, we have other people that this person's connected to, and we're just describing that with connected to. Very generic. And then you would qualify on the properties of these relationships. To the right we have the inverse, which is the fine grain model. So in the fine grain model you have all of the extreme of that is that all the relationship types are completely different. And they describe more accurately the connections between the people or the addresses of the product. So some examples here is the first thing Peter bought on eBay is a relationship type. I don't advise you doing that, but that's just an extreme example. So again, if you wanted to qualify by a property and you have these general relationships, it can be a very good idea. For example, if you have Peter and the addresses that are attached to Peter, to just use address. And then when you're querying, you can actually just specify this pattern, which is just Peter, relationship type address, and then the addresses. And then you can then filter on a property which qualifies it, here being type. So that is the coarse grain. And then the fine grain has two different relationship types for address. You have work address and you have home address. So our guideline here is that, in this case, it's best to use both. That gives you the best expressivity with Cypher to be able to actually go and query these things. You can use either or. Okay, cool. So that's all the graph data modeling guidelines I have for you today, but I wanted to introduce you to a project that developer Evangelist at Neo4j have been actively working on to help you kind of understand your data model, to see what other people are doing, if somebody shares a similar domain or a use case, to allow you to go on a website, be able to find some interactive kind of white paper or a blog post, is the way I describe it, that shows how they solve the problem and maybe how it's different from yours. So we call this the Neo4j Graph Gist project. And here we have this really another pretty graph, which our intern May created recently. So we have gist, and we have a use case associated with the gist. We have a domain that the use case is within. And we have people who have authored the gist. And then two, we're tracking the amount of times somebody's tweeted this on Twitter. So that's just an example. And so May's created an actual graph gist of gists, which is really clever. So what about authoring a graph gist? So first, you want to start by articulating your problem. So you look at your domain, you look at your use case, you articulate it. You probably have already articulated it many times, but so it should be fairly easy for you to articulate that in an actual kind of blog post format. So I'm going to go ahead and pull up our graph gist project page. So it's at gist.neo4j.org, and here you have a quick introduction. We have a video which shows you kind of how to get started, how do I author a gist, and then we have some examples. So I'm going to show you an example I created on bank fraud detection using Neo4j. And so here's the basic format of a graph gist. So you have some table of contents here. And then you start by introducing your problem. So just a quick paragraph here. Zoom in. So you see the introduction that I have is banks and insurance companies lose billions of dollars every year to fraud. Traditional methods of fraud detection play an important role in minimizing these losses. However, increasingly sophisticated fraudsters have developed a variety of ways to elude discovery, both by working together and by leveraging various other means of constructing false identities. I'm not going to do that for the rest of the gist, but that just gives you an idea of an introduction. So then you want to go through explaining your scenario, some of the various aspects of your scenario. For this example, I took a white paper that was actually authored by a colleague of mine on this scenario, and I turned it into a graph gist. And so I go through, I explain the scenario, And I talk about how graph databases can help. So exactly how do I plan to, in this case, identify fraud rings, which is an attribute of the fraud in this first-party bank fraud. So here we have this graph data model that I've constructed that describes that. So here we can see that we have various account holders and that they have some piece of their identity is also a node. So for example, we have an address, we have a social security number, we have a phone number, and these people, these account holders, are sharing some aspect of their identity. And so a graph database is great because it allows you to traverse and find these rings using some pattern detection and then to identify what's the risk involved. So you model out the domain of your problem, you put the entities that are required to answer your questions and solve the problem. And then you go ahead and you create a Cypher dataset, or Cypher query that creates the sample dataset to allow you to, well, here's a visualization of that graph after Cypher created it. But then the point of that is to run some queries on it. So we're allowing you to create this markdown file that renders into this web page that creates a sharded instance of our database in its most current version, and then you can write some queries against that, again included in this markdown file. So here I'm answering the question, I'm saying find the account holders who share more than one piece of legitimate contact information. So you can see that ring here. It says Jane, John and Matt, they live in San Francisco. They have Jane and Matt share a social security number. So I want to identify that with a query. And so we see here that the fraud ring is John Doe, Jane Appleseed, and Matt Smith. And we see that they share the contact type address and the size of the ring. So then the next thing is to ask the final question, which is to determine the financial risk of a possible fraud ring. And the result is that it just takes a bit of the previous query, but adds in the financial risks by doing an aggregate on the sum of their bank accounts that they have in their credit lines. Cool. So that's the GraphGIST project. Cool. So summary of GraphGIST. So introduce your problem, explain the solution, design a graph data model. It helps to start with a whiteboard there, translate that into an image if you want. Take a picture of it. And then from there, translate that graph data model into a Cypher dataset. And then formulate some of these questions that you propose to solve the problem. And translate those questions into Cypher queries that you can run against your graph and see the results. And then the most important part of this is that it allows you to quickly iterate without too much overhead by changing a markdown file and then refreshing the page. And you can iterate through that and see how changing a Cypher query might impact the final result. Again, you can get started with that at gist.neo4j.org. And that concludes today's talk. So thank you, and I will open it up for questions. Okay, so any questions? Graph data modeling, GraphGIST? Sure.
I had a quick question about, so when you were graphing the movies and actors,
yeah.
So say Clint Eastwood is a director and an actor, would you label him a person and a director, or, I mean, an actor and a director?
So I think we actually have, yeah, we actually have Clint Eastwood in here, and I think we actually have an answer to that. So, no, so you would just have person be the label. In the sample data set, we're not actually applying actor as a label, or you could do that. That's another subset. But I think here if we match on, I think Aaron Sorkin, so if I do person, name.
So whether or not they're a director would just be an actor or a property?
Yeah, so it would be a relationship type. So if you have directed movie, oh, this works. Sure. I spelled it wrong. Is it 2 R's? No.
The name, capital N.
I'll just do it. The name what?
The name of Aaron name, the key is capital N-A-M. Case sensitive.
Yeah, it should be good. Cool. So in this case, what you can do is use regular expressions. So if I do where, and then I do p.name, and then I do equal mark, right, equal, and then squiggly, I can actually do regular expression pattern, find sorting. Or directed by is probably the issue. So live coding for the win.
Person directed by.
I feel like I don't want to admit defeat, but yeah, I'm not going to admit defeat. Screw that.
Wouldn't
You
it
guys
be
can stay here. You're
directed
not
by
going to leave,
person,
right?
so the other way around?
Okay, so best I can do is to look at all of the movies or directed
Why
relationship.
do you add the directed by? It's not when you're searching what's happening.
So, okay, so you can actually open up this tab here, which shows you some of the information, like the relationship types. So I was actually right first time it's directed. Yeah.
It's he acted in something and he wrote something.
Right.
I'm looking at the sample data set now.
Okay, cool. Yeah, so too, if you click one of these, you can say directed, and that's just going to pull up the sample query. But yeah, so what are some movies that Aaron Sorkin, Social Network? I don't think that's in here.
He acted in A Few Good Men and he wrote
A Few Good Men, yeah. Did you get a book? Do you want a book? Do you want some swag for helping me?
Sure.
Okay, so the title is A Few Good Men. Okay, cool. So we have the movie A Few Good Men now. If I double click on it real quick, I can see there he is, Aaron Sorkin. Now, in our visualization, you can't really see it because they're overlapping, but you have a directed and you have an acted relationship here. And so that's how you would differentiate between the two in this data set. But you could also use labels as well. Those two questions. Yeah.
Cool.
Thanks for being patient. Okay, other questions? Yes, in the back.
I see a lot of ways to choose how to model your data. Like you can apply labels to things, but you can also make relations to a node which is actually a label. Like, for example, I can label people with being a director, or I can make a node director, and or I'm a bit used to RDF, I guess. For this
Yeah.
So I would have this person, and then a relation that is like is a and connected to the node director, for example. That's one way to do things in there. I see with all your examples, like whiteboard example, I think yeah, you can do it this way, you can also do it another way, and I think to know which method to choose, one thing, isn't it important to know what are the implications for indexing and the speed of like finding things back?
Right. Very good.
Can you say something about that? Like, what's the difference between labeling something or connecting it to a node which you use as a label?
Right.
And stuff like that.
So in that example where you have, again, labels that mark some subset of the graph that allows you to limit the amount, the search space that a Cypher query is going to go over. And so that's the advantage of using labels, and that's unique to Neo4j. So in the RDF model, you have this I think it's a coarse or fine grained model where if you're connecting, you have a link to every other node which is exact. And so those are some of the differences. In traversals, you can have multiple relationships that are the same, and then you can qualify by property of that relationship. And there's an inherent performance advantage here in the property graph data model, which you couldn't apply to the RDF world because RDFs are just so different as far as the way that they work. But I do see what you're talking about as having a node as directed. We call that an intermediate node. So if you wanted to do something like a hyperedge, which is a relationship that's attached to another relationship, we don't allow you to do that with the property graph data model, but we allow you to create a node that connects two other nodes, and we call that an intermediate node. Then you can have more relationships spawn off from that.
How are things indexed? But for one moment, you suggested to have both the work address and the home address as two different types of relations, and to have a relation address with the properties home and work.
Yeah.
Like, I would think like I want to just take one of these, like preferably the latter, and then have my graph database figure out how to index it, so it can also quickly find one of them. Like, isn't it silly that you have to manually say that there's a work address and a home address as a particular, like what would you want to
I think it is silly, to be honest, in my opinion.
purely for, like, am I correct at all that this, doing it that way is purely for the sake of speed of finding things back?
So this slide specifically, this best of both worlds, is really specifically for formulating Cypher queries. So you have, your DBA, maybe you created this loose optional schema, and you want to give business users who might be creating Cypher queries a more expressive way of saying certain things and saying.
But you can express it still if you don't have these two extra types of relations, right? You can still say, I want somebody, I want everybody who has this address with where the type of the address, the property has the property that it's worth. So, where it has the property that the type is worth.
Right, so
Right.
there's two ways to formulate the Cypher query, right? So if you wanted to get all addresses of a person, if you wanted to answer that question, well, if you just had work address and home address, then you'd have to specify both of those within a work to separate. With just having address relationship type, you can get all the addresses, and then you can further filter that down by the type.
Yeah.
So that's how you would use this model to do it. But if you just wanted to find the work address, say your web application, maybe e-commerce, just wants to find the work address or the delivery address, then the Cypher query can just say, person, work address, and then address, as opposed to having a filter on the type.
Yeah, but, like, so is it just for the convenience of being able to write it?
It is absolutely about convenience, yeah.
Okay.
That's just the guideline. You don't have to do that, of course, but it's showing you that you can use both the coarse grain and the fine grain models. Question,
Just quickly, another thing that just occurred to me is you could have the address nodes, be address labels, and then it could be like Peter lives at address, Peter works at address.
Totally. Yeah, it's a good way to represent it.
I was wondering if you could have indexing relationships, like say Peter has 1,000 addresses, right? And you wanted only the type work addresses.
Yeah.
And you have an index on the type attribute of those relationships to optimize those types of queries.
It's a good question. No, we don't support indexing for relationships because you would usually start at a node. So you would index that node. You would then, in that case, if you had that scenario, maybe you're Bill Gates and you do have 1 million addresses, but you would actually use an intermediate node and then index on the intermediate. So an intermediate node is like this idea of a hyperbridge where you have 3 nodes. You have a person, and then the address is a node that they're connected to, and then that's connected to other nodes. So you have these 3 nodes connected by 2 relationships. And then you would index on the address to further create a subset of that.
Can you have here, still here, multiple levels on a relationship?
Yes.
Say the address and work address.
Right.
You have one edge and 2 levels, and then both of the queries with one relationship.
Right, yeah. So you have 2 queries which are really different. Work address, home address.
I mean, on one relationship you have 2 levels.
Yeah. Yeah, I think Cool, any other questions?
I was trying to find some benchmarks from Neo4j compared against like MySQL and other SQL databases, and also against other graph databases, but I couldn't find many sources. So how do you think that Neo4j compares against those other databases? Because I imagine that Neo4j must be good for some situations, but not so good for other situations. And what cases do you think that Neo4j is better against MySQL or other graphs?
Yeah, so the reason why you probably can't find any benchmarks is because what a graph database allows you to do is to do some difficult things in SQL easier. So in MySQL, if you were trying to do this, try to formulate a query which is friend with friend, or just n steps out, n hops, you have to dynamically generate that query to the depth that you're looking for, right? So the benchmarks, they differ depending on the query that you're actually doing. So let's say it really depends on your use case. We do have benchmarks for Neo4j. We have benchmarks for Neo4j against other graph databases. We have benchmarks for Cypher, which is different than our Java API. So they are available, and I can help you out towards if you're looking for those. Yeah.
I've seen that graph X, they treat differently the nodes who are highly connected to the nodes that are more independent. Do you do these kind of things?
Yeah, so like clustering.
No, they have some nodes which have a lot of relations.
Yeah.
Okay, which are a few nodes which are highly related, and they will treat them differently in the engine for performance sake.
Okay, for execution planning.
Yeah.
We don't have that available in Cypher today. You can create your own imperatively using the Java API. I don't recommend that, but in the future we do plan to. We have on the product roadmap to take advantage of some of these statistical distributions to improve query time execution. Yeah. Good question. Cool. Any other questions? Cool. Go up front here and then back.
Which verticals find maximum uses?
Sorry, say it again.
Which verticals find maximum uses of graph database?
Magazine what?
Which verticals? I mean, in which businesses like?
Oh, some of the industries that use. Yeah. Good question. So, if you go to neo4j.com, this is a new website that we recently launched that really, when we asked ourselves what do we want to articulate about our database, it's really our customers. So if you go to use cases here, you can see some of the popular use cases like network and data center management, social recommendations, identity and access management, and geo. So I'll just go, let's go to network and data center management. So here you can just get more information about some of the customers that use this use case specifically, like HP is a good example. And then you can also see some user stories. So all of the resources are here. Those are the 5 big ones.
Kenny, does this also have the eBay now case study that talks about performance? Actually, they were running on MySQL, by the way. And that's an interesting use case that talks about performance. In fact, their use case was that they're a same-day delivery service, and some of their physical deliveries, the truck taking a package to, was happening faster than some of their queries running on MySQL. And they moved to Neo4j, and those queries were returned back in MySQL.
Right.
It's essentially about connected data. Wherever you have connected data, that's where you will see the benefit of a graph database.
Absolutely, thanks, Fixit. Yeah, so if you go to Shuttle, which was acquired recently by eBay, you can look at the slides here, which kind of tell that story. Also, there's videos out there. If you're interested more on that, I can help you with the resources and content afterwards. Was there a question in back? Yeah.
There are a lot of cases where people already have a lot of data in the relational databases, but would like to also perform certain graph queries.
Right.
So do you have any recommendations for how to, in real time, translate RDBMS data into Neo4j so that it can be good?
Yeah, so you kind of want to use it as like a supplemental thing that attaches to your relational database.
Right.
There's really no way that we support that kind of feature. You actually would have to import it, do some ETL process. We have a lot of import options. We have online import, offline import. And so for that example, something I might do is to create an ETL, run that the data from that ETL in memory on Neo4j, spin up an instance, and then start doing some queries. And then when you shut down an instance, then none of the data is persisted to disk, it stays in memory. That's the way that I would probably approach that problem. Any other questions? Awesome. Well, thank you so much for coming and listening to me today. And if you're interested in getting in touch, here's my contact info. And then I'll stick around for a little bit for questions offline. Yeah.